Hello everyone, my name is Farrell Liam with the student number 210-553-1089. Today I'm going to explain about machining processes, chapter G to chapter J. The main reference from this presentation is from Handbook of Manufacturing Processes, How Products, Components and Materials Are Made by James G. Brala. I'm going to explain 4 chapters today. The first one is sewing, flame cutting, electrical machining processes, and finish machining operations. Okay, let's get to the next one, sewing. Circular sewing. Circular sewing operation uses a saw in the form of a circular disc with cutting teeth on the periphery. As the circular saw rotates, it is fed against the workpiece, machining a narrow slot in the workpiece and eventually severing it. The workpiece is fed directly into the saw. Circular saws for metal cutting are sometimes called cold saws because they don't significantly hit the workpiece as friction saws do. This is the video of the circular sawing. The man is sawing a wood workpiece. This is the circular sawing. Okay, let's get to the next one, band sawing. This operation is most commonly a cut-off operation. Instead of a circular disc, the saw is an endless steel band with cutting teeth on the edge. The blade moves as it cuts in one direction. This is the blade, and this is the workpiece. Okay, cutting is continuous and blade wear is uniform over the whole length of the blade. This is the example of the video of band sawing. This is the workpiece and this is the saw. As you can see, the workpiece is fed manually into the saw. Okay, the next one is contour sawing. Contour sawing operation uses a band saw. The power band normally moves vertically downward and the workpiece, resting on a horizontal table, is fed into the moving blade either manually with or without power assist, or automatically into the moving blade. The cut can be in a straight line or a curved path, depending on the shape of the part to be produced. Hack sawing. Hack sawing uses a reciprocating, either manually or mechanically operated, to perform a cut-off operation. Cutting takes place only on the forward stroke. This is the mechanically operated hacksaw, and this is the manual hacksaw. Blades and equipment are less costly than those used with other sawing methods. The next one is abrasive sawing. Abrasive sawing uses a circular band or reciprocating saw blade with a cutting edge that consists of abrasive particles rather than teeth formed in the edge of the metal blade itself. Surface speeds are much higher than with conventional sawing. Abrasive sawing used for hard materials or difficult to cut. Coolant may be used to improve the finish. This is the illustration of abrasive saw, and this is the abrasive saw machine. Next one is diamond edge sawing. This diamond edge sawing is a kind of abrasive sawing that uses diamond abrasive particles because of particular hardness of the workpiece material. As you can see, the edge of the saw is formed like a diamond. In this operation, cutting of ceramics, glass, stone, carbide, hardened die steel, nickel and cobalt alloys are typical applications, and sufficient coolant and accurate feed control are necessary in this operation. This is the video of the diamond edge sawing. diamond edge saw and the command gate. In this operation, diamond edge saw can cut into the hard materials like ceramics. Friction sawing. This operation uses an extremely high-speed saw blade that softens or melts the workpiece material with frictional heat. The cutting teeth then remove the softened material with a cutting action. The movement of the blade prevents it from overheating since any one part of it is in contact with the hot work for only an instant. The process is suitable for hardened materials. The illustration is similar to abrasive sawing. The difference is the friction sawing is the edge. The edge of the saw in friction sawing operation, it's like this. This is an example of friction sawing operation. Okay, let's get into the next chapter, flame cutting or thermal cutting. The first one is oxy-fuel gas cutting, OFC. In this operation, it uses acetylene, natural gas, propane or hydrogen in combination with oxygen to fuel the process. As the torch moves, a narrow slit is made in the workpiece. Parts are most commonly cut from flat plate. Shipbuilding, construction, tank, pressure vessel, and heavy equipment manufacture are industries that use the process. Straight or beveled cuts can be made, and welding is a common subsequent operation. This is the illustration of oxy-fuel gas cutting. This is the preheating, and the process starts from here and end. This is the example of the oxy-fuel gas cutting operation. And that is the result of this oxy-fuel gas cutting. This is the result. A metal tube. Next one is metal powder cutting or POC. Metal powder cutting is a method applicable to metals that do not flame cut very easily. Preheated iron powder is injected into the flame to raise the cutting temperature. Oxidation of the iron provides an aid to cutting metals that are highly resistant to oxidation. Chromium, nickel, stainless steels, high alloy steels, and cast iron are cut with this method. It is also removes gates and risers from iron and stainless steel castings, and to cut stacked sheets or plates more easily. This is the illustration of the metal powder cutting. Chemical flux cutting or FOC. In this operation adds flux to the cutting gases to make the metal oxide more fluid and more easily removed from the gap of the cut. Powdered chemicals such as sodium carbonate and other salts of sodium are used. This is the workpiece. Arc cutting. Arc cutting operations involves a group of processes that use the heat of an arc to melt a metal workpiece to sever it or remove metal. All common arc welding processes can be adapted to metal cutting as well as metal fusion. When arc processes are used to cut steel, oxygen may be used in conjunction with the arc to support the oxidation. There are some of the arc cutting. The first one is plasma arc cutting. Plasma arc cutting operation uses the extremely high temperature of the plasma arc to melt the workpiece metal. Severing is a result of melting rather than oxidation. The process provides very high cutting speeds, 4 to 5 times higher than those achievable with standard oxyfuel cutting. This is the illustration of plasma arc cutting. This is the workpiece, electrode, nozzle, outer nozzle, cutting glass, gas, and this water shield. There is an example of plasma arc cutting. Just only like this, and it cuts the workpiece metal. The next one, the second arc cutting, is air carbon arc cutting and grooving. In this process, intense heat from an electric arc between the tip of the carbon electrode and the metal workpiece melts workpiece material. A high velocity air stream passing through the arc blows the molten metal away from the area of the cut. This process used to remove screws, runners, risers, and fins from castings. Cast iron, steel, stainless steels, ductile and malleable iron, nickel, aluminum, copper alloys have been processed with this air carbon arc cutting and grooving method. The next arc cutting is oxygen lens cutting or LOC, also known as oxygen arc cutting, used in steel mills to sever materials that is already hot from the steel making process. A small pipe carries oxygen to the workpiece, which is hot enough to start the oxidizing reaction without the need for further heating by fuel. This is the example of the video, oxygen lens cutting operation. Okay. The fourth of arc cutting is gas metal arc cutting. In this process, the heat is provided by an electric arc between the workpiece and a continuously fed metal wire, shorted by the flow of an inert shielding gas. This method is not highly significant in industrial production situations. This is the illustration of gas metal arc cutting. The fifth of arc cutting is gas tungsten arc cutting. The arc melts workpiece metal, which is forced out of the cut by gas pressure from the shielding gas and the effects of the arc. This process is used for cutting stainless steels and various non-ferrous metals, including aluminum, copper, nickel, magnesium, silicon bronze, and copper nickel. The next of arc cutting is shielded metal arc cutting. This operation is similar to stick welding, when that method is used to cut the workpiece rather than to fuse it to another member. A metal electrode in rod form coated with flux is used without any gas jet. The heat of the arc of high current density melts the workpiece, and gravity is used to carry away the molten metal. This is the illustration of the shielded metal arc cutting. Okay, carbon arc cutting, another arc cutting operation. It's not a significant industrial process, but is found in small shops that lack more equipment. The arc between a carbon graphite electrode and workpiece melts the workpiece where the arc contains it. Gravity and pressure of the arc rather than the air jet used with air carbon arc cutting removes the molten metal. Okay, let's get into the next chapter, electrical machining processes. The first one is electrical discharge machining, also known as spark erosion machining. This process uses electrical discharge or sparks to erode the workpiece material. The discharge passes from the tool to the workpiece. The workpiece material, which must be electrically conductive, melts or vaporizes at the point where it is touched by a spark. The rate of cutting and surface finish are controllable by varying the frequency, voltage, and current in the electrical pulses. For example, higher energy levels produce faster erosion of the workpiece but a rougher finish. This is the illustration. This is the workpiece. Video example of electrical discharge machining. This is the process of electrical discharge machining. Okay, the next one is electrochemical machining or ECM. Electrochemical machining removes a metal by a reverse electroplating process. The workpiece becomes the anode and the tool is cathode of the electrolysis process. A highly conductive electrolytic fluid is pumped into the space between the workpiece and the tool, and high amperage current removes workpiece material by anodic dissolution. Temperature control of the electrolyte, control of the gap and feed rate of the tool, and maintenance of electrolyte cleanliness are important elements in the process. There are some electrochemical machining. The first one is electrochemical grinding. Electrochemical grinding process is similar to electrochemical machining, but replace the relatively stationary tool with a rotating conductive grinding wheel. This is the rotating conductive grinding wheel. The wheel normally consists of aluminum oxide abrasive bonded to a metal wheel, which acts as the cathode of the electrolytic circuit. The advantage of electrochemical grinding operation is relatively high metal removal rates for hard metals, freedom from heat damage to the workpiece, and the ability to grind fragile parts. The second one is electrochemical turning. The workpiece rotates as in conventional turning, but the cutting tool is replaced by an electrode. Electrolytic fluid is directed to the gap between the tool and the work, and material is removed by electrolytic action between the workpiece and the electrode. Okay, the next one is electrochemical discharge grinding, ECDJ, also known as electrochemical discharge machining. It is a combination of electrochemical grinding and electrical discharge grinding. The process is used in the grinding of carbide cutters. It can also be with hardened tool steels, nickel alloys, and parts that are heat sensitive or fragile. The next one is electrochemical honing, ECH. This process is electrolytic action added to a conventional honing, and is quite similar to electrochemical grinding. Material is removed from the workpiece by a combination of electrolytic action and mechanical abrasion. The electrolytic action removes most of the material, and the abrasive action of the honing stones removes the oxides produced by the electrolytic action. This is the illustration of electrochemical honing process. Electro-etching is a method for marking workpieces that are electrically conductive. A stencil is placed on the workpiece, and a pad containing an electrolyte is placed or dabbed on the stencil. Electro-etching is normally performed manually and is a suitable method when production quantities are modest. The last chapter today is finished machining operation. The first one is honing. Honing is a low-velocity abrasive machining process. One or more bonded abrasive stones are put in area contact with the surface to be machined. Slow movement of the sticks or stones in several directions abrades the high spots on the workpiece surface and makes the surface smoother and more true. Because of the slow movement, there are no heat effects to the metal surface. The next one is lapping. Lapping operation, it utilizes a fine abrasive in paste or powder form, which is contained between the workpiece and the lapping tool. The lapping tool is made of materials softer than the workpiece and is shaped to mate with the surface being machined. The purpose is to remove fine scratch marks or to create very flat or otherwise smooth and precise surfaces. This is the example of lapping. Give it to the process. Okay, the next one is super finishing. Super finishing operation is a solid abrasive is used, but it loosely bonded so that it wears to the shape of the workpiece surface. A controlled bidirectional movement of the workpiece and the abrasive under light pressure removes high spots and smooths the surface. Removing surface material that has been smeared or distorted by prior grinding or machining. Automotives, crankshafts, camshafts, bearings, brake drums, and distributor shafts are typical superfinished parts. This is the example of superfinishing operation. This is the workpiece and it rotates, and this is the stone holder and it gives pressure into the workpiece. This is the example of the video. The workpiece rotates and the pressure fed into the workpiece. The fourth finished machining operation is burnishing. Burnishing operation means of smoothing machined or other surfaces by rubbing a smooth, hard object against the surface with considerable pressure. Burnishing is not a machining operation, but instead deforms and presses down localized high spots from cutting tools and thereby smooth rough areas. There are some of burnishing operations. There's ball burnishing and roller burnishing. Now this example videos uses a ball burnishing tool. It slowly smoothens the workpiece material. Okay, the last one is roller burnishing. Roller burnishing operation refines the surface of a workpiece by pressure rolling rather than by removing metal. The burnishing tool incorporates one or more hardened, finely polished rollers which bear against the workpiece at high pressure. Typical parts that used in roller burnishing is valve stamps, piston rods, turbine shafts, pump plungers, and rolls for the plastic and paper industries. Now this is the video of roller burnishing. Okay, this is the roller, and this is the workpiece materials. Okay, thanks for today.